Okay, so today I'm going to discuss about conservation of energy, which is the last section of chapter 5. So the conservation of energy means the total amount of energy of a system will not change, or in other words, it stays the same, right? So I'm going to show you or discuss that with two examples. So the first one is, let's take a bulb, right? And electric current is passing through that and going through a filament and coming out, right? So let's take the energy input and the energy output, right? So we know, suppose you measure the energy input, right? So which is electrical energy. So it is going to be converted into light plus heat energy, right? So but when you measure the initial energy and then the final energy or the output and input, the output energy will be less than the input energy. Why? Because some of the energy will be wasted as heat, which we cannot measure, right? So now assume that you have a boundary, right? So through which the energy cannot pass through, right? So all the energy will be inside or confined into this boundary. So now you measure the input energy and the output energy, because now you can measure the heat, light, all types of energy. So you will get the energy input is equal to energy output, right? So now let us define a system called isolated system. So the isolated system means a system with a boundary, right, through which, so it has a boundary through which energy cannot pass, or any other energy cannot come into that, right? So such system is called isolated system, and in that always the total energy input is going to be the total energy output, right? So now I'm going to show another example. So example 2, let's take, there is a table, right? And you have a book and the table is rough, right? So you push it with an initial velocity Vi. So it goes and there is a friction force and it will stop somewhere at distance x. Right? So, while the book is sliding, there will be a friction force. So, there will be a heat generated due to the friction force. So, when you take the system, it's just the book. So, when you measure the input or the initial and final energy of the book, definitely it's not going to be equal. Then take the system as just the table, right? So even now, when you measure the initial and final, it is not going to be equal because we are not measuring the temperature. But now think that the system is the book plus table, and you have a boundary where the energy or any type of energy cannot escape, right? Then we can say in this system the initial energy is equal to final energy, right? So by using these two examples, what I have given to you is an idea of an isolated system in which the initial energy is equal to final energy, or in other word, I can say the energy is conserved, right? So at this point, you have to pause this video and go to the chapter 5 PowerPoint slide and go through the PowerPoint slide number from 38 to 43. Right? After going through that, then you can reassume the video and you can continue. Now the next thing, let us derive an expression for the conservation of energy, or an equation for conservation of energy, right? So for that, I'm going to take the example we used that before too. So what I'm going to do is, there is a book. This is the ground. So let's take the height is y initial. So you drop the book. So the book is now at this level. So which is from the ground, the height is y final, and the difference is delta y, right? And you know, the only force acting is the gravity. So what I'm going to do, the work done by gravity, so we learned that under potential energy, which is negative change in potential energy. So this we learned under potential energy, right? Also, we learned work kinetic energy theorem. So the work net is equal to delta KE, right? So we know the work net is only due to the gravitational force. So I can write the work gravity is delta KE. So work gravity is this one. So I can write delta KE is negative change in potential energy, right? So now I can rewrite like adding this part both sides. So PEG become 0, right? So change in kinetic energy plus change in potential energy equals 0. That means the initial and final is going to be equal. But this result is true for any type of potential energy. So the another potential energy you learned is the spring potential energy. So it is true for any type of, it can be spring or gravitational potential energy. So I will rewrite as a general equation plus delta PE, which is 0. So delta means change. So I can rewrite that KE final minus kinetic energy initial plus potential energy final minus potential energy initial, which is 0. So I can rearrange them. Okay, which is equal to plus potential energy initial. So usually we write initial first. So I would just flip it. Kinetic energy final plus potential energy final. So this is the expression for the conservation of energy. right? So change in kinetic plus change in potential 0. So we will come out like the initial total energy, which is given by kinetic and potential, is equal to final total energy, which is by kinetic and potential. So here the things that you have to remember is we are using only conservative forces in the system. So the forces in the system should be conservative, which is gravity or spring force. And when you deal with the energies, you will see we are only going to talk about kinetic energy, potential energy due to gravity, potential energy due to spring. So whenever you see a non-conservative force like friction, or sometimes an applied force by an external agent, so if you have these, then you cannot use the conservation of energy, right? So remember, these are some restrictions to use the conservation of energy, right? Because in the sections or the equations that we are using in this section, we are not going to calculate the heat dissipated by frictional force. So we are going to restrict with these type of forces and energies, right? So in my next video, so I will stop here, right? So in my next video, I'm going to discuss some examples. Okay, thank you.